Hello again, everybody, and welcome back. We are getting towards the end of our chapter on work and kinetic energy, and this last little segment right here is on power. Um, a lot of people don't know what power is. A lot of people like power, but they don't know what the definition of it is. Power is the ability to do work at a certain rate. If you were to lift a rock up off the ground, all right, or let's just say just a heavy box, all right? You've got a heavy box on the ground right here, and you lift it up. It's not a very good ground. Sorry, let's try my box again right here. There's the ground, and you lift it up to a certain height, okay? It requires a certain amount of work, right, to do that. But what if you were to do that, to lift that box up really rapidly, very, very quickly? All right, you do the same amount of work, but you do it in a much shorter amount of time. And what that means is you have exerted more power. It is the time rate at which work gets done. It's a scalar quantity. You can't have negative power, just like you also can't have negative energy. But it is it's the work that it's work done over a certain amount of time. So this right here, work over time. That's not a good highlighting color, is it? I'll do that in red. Work over time is our definition of power. And of course, you know, work is measured in joules and time is measured in seconds. So it could be joules per second. It's also known as force times velocity. You could think of power as force times velocity as well. Well, why on earth does that work? Well, remember that work is force times distance. And if you have work being force times distance, that per second, instead of saying joules per second, you could say that is newtons times meters per second. Does that make sense? This right here, distance per second, or displacement per second, is velocity right there. So power is force times velocity, or work divided by time. Both of those are the same thing. So in this case, the units would be Newton meters per second. And really, a Newton meter is what a joule is right there. But those are two ways of determining power. The unit for power is a watt. 1 watt is a joule per second, or a Newton meter per second right there. All right. Another unit, oh, by the way, real quick, watts are what we measure light bulbs in. It's probably one of the most common definitions of, not definitions, but you might say household applications of a watt. But if you look at almost any object in your in your house that requires electricity or that requires power, somewhere on the back on some sort of sticker there will be some sort of an indication of how many watts that it consumes, how many watts of power it consumes. Another way to measure power is in what we call horsepower. Right, now, horsepower is not necessarily how many watts an average horse, can put out, although it was developed by somebody in the Industrial Revolution when they were trying to compare how much power maybe a steam engine could put out versus an equivalent amount of horses. And they came up with this idea that 1 horsepower is 746 watts. So this is really just a conversion right here. But when we find power in watts, this is our conversion to horsepower. 1 horsepower is 746 watts. Just to give you an idea of how many watts certain things put out. Again, remember, a watt is a joule per second, or a Newton meter per second. Think of raising a Newton up a meter per second. That's what a watt is. Here is a list of a few things that produce a certain amount of power. Hoover Dam is one of the more, you might say, productive hydroelectric dams in our country. It's just below, I think, the Grand Canyon. No, I'm sorry. It's just above the Grand Canyon. And so it holds back the whole Colorado River, and all that water pours down through the dam and turns generators that turn out electricity. This creates 1.34 times 10 to the ninth watts. That's 1.34 billion watts, or you could say gigawatts. Gigawatts. If you recall from Back to the Future, they called it gigawatts that the DeLorean required. 1.21 gigawatts. So the Hoover Dam produces just a little bit more than the whole Back to the Future time traveling DeLorean requires to run. All right, so that's a lot of power right there. All right, a car moving at 40 miles per hour. Now this is you might say an average car, somewhere in the realm of 7 times 10 to the fourth watts. So that's 70,000 watts. A home stove. All right, so that's it's 12,000 watts right there. Sunlight falling on 1 square meter. This is interesting. 1,380 watts. So if you think of what a 100 watt light bulb looks like, that's pretty bright. So that's like 13 of those, right? Sunlight falling on 1 square meter. That's a lot of power, a lot of energy that we can extract from sunlight. Sort of gives you an idea of what the potential is in photoelectric, like solar panels. All right, a refrigerator, 615 watts. All right, TV. Now this is let's see, this might be before LED TVs. LED TVs require a lot less power, but this might be an old tube television right there, 200 watts. You walking up the stairs in terms of power. Even your brain puts out a certain number of watts worth of power. So all these things require or produce power. And if we're clever enough, we can figure out how to harness that power. Very much like we figured out how to harness the power of falling water at Hoover Dam. All right. Well, this is the last segment or so of our chapter, and so I'm going to do this last example together with you, and then that'll be it. All right. So let's find out about power. Let's calculate power in this final example right here, and that'll be it for our chapter. All right. First thing I'm going to do is I'm going to shrink this down because I know I'm going to need a little bit more room right here because this picture's taking up the whole thing. All right, so I'm going to shrink that down right there. Okay, and I'm going to move it over into the corner too. All righty, to pass a slow-moving truck, you, in your car, that is, you want your car that has a mass of 1.30 times 10 to the third kilograms. All right, so the mass of the car equals 1.30 times 10 to the 3 kilograms. So if you move that over 3 points, that's 1,300 kilograms, right? You want a 1,300 kilogram car to accelerate from 13.4 meters per second, all right? So that sounds like an initial velocity, right? 13.4 meters per second. Ignore the miles per hour because we don't care about that. That's English units. From 13.4 meters per second to 17.9 meters per second. So that is the final velocity, 17.9 meters per second. Okay, and to do it in 3 seconds. So time equals 3.00 seconds. Question is, what is the power required for this pass? Okay? Well, let's ask ourselves right here, what is the definition of power? You can think of it as 2 ways. It could be work, or power equals work over time, or you could say that power equals force times velocity. Well, we do have some velocities right here, but we don't really have a force. All right? So I'm thinking we're not going to be using this version, but we are going to be using this version right here because we do have time. Now the question is, what work was being done? Power equals work over time. Well, we do have some velocities, and we do have a mass of the car right there. What does that tell you? What kind of energy value does velocity and mass give you? Well, we know that kinetic energy, capital K, equals 1/2 mv squared, right? Okay. And we also know from our work kinetic energy theorem that the work that is done equals a change in kinetic energy, which is K final minus K initial. So why don't we take that, and now I'm kind of really sorry I drew that other equation in there that we didn't wind up using. Let me sort of try to erase this here. There we go. I'm actually not really erasing it, I'm drawing over it with white, but same difference. All right, and so we're going to take this and put this in for our work right there. That the work that is done by the car is really represented by that change in kinetic energy over time, right? Well, of course, change in kinetic energy is K final minus K initial, all over time. And let's expand out those K's right there. Kinetic energy final, that is 1/2 mass of the car times velocity final squared minus 1/2 mass of the car times the initial velocity squared, all that divided by the time that it takes. Okay? It appears that I didn't, I left enough room, I think. I'll just write it down below. All right, well, let's find out what we have. 1/2 mv final squared. So 1/2, instead of 1/2, I'm going to put 0.5. 0.5 times the mass, so that's 1,300 kilograms, right? V final, that's 17.9 squared, minus 0.5 times 1,300 times our initial velocity, 13.4 meters per second. That value squared over the time, which is 3.00 seconds. And sure enough, I'm still going to have to shrink that down a little bit for a little more space. This is for our final answer, however. Okay? Oops, didn't mean to do that. I'm going to bring this back down here. And what's our final answer going to be? I get an answer of 30,518. Ooh, not joules. We want watts, right? Watts. Now, if you use significant figures, a lot of those will cancel out. So it would probably be something more like 3.05, I believe, times 10 to the 4th watts. That's probably more accurate, all right, because those other units will cancel out. But that's a lot of watts right there. That's a lot of power for your car to go from this velocity to that velocity and drag the whole mass of the car, and probably its occupants too, with it. So that power is 30,000 watts right there. So that's a good use of power being work over time. It's also a good use of our work kinetic energy theorem. Work is a change in kinetic energy. Put that over time, and that gives you the amount of work that was done per time, which is our definition of power. So that's going to be it for example 8.8, and it's going to be it for our chapter, because that's the last segment right there. So if you have any questions, please make sure you see me. But in the meantime, thanks for following along once again, and I'll see you on the next one.